Hey everyone, so let's continue our study of Taylor polynomials. Remember last time we had t sub n of x, right? That's going to be the sum n equals 0. Instead of going to infinity, we go to capital N, right? And then it'll be the nth derivative evaluated at a divided by n factorial x minus a raised to the n. So this is the order n Taylor polynomial at capital A. And the idea here is that t sub n of x is a degree n polynomial approximation of the original function f of x, right? And what we want to do, we're going to be studying the question of, how good of an approximation it is and how do you ensure that you actually have a good approximation, right? So we'll take a look at that later on. Let's do some computations now. So let's start off with cosine, right? So let's find the order 3 Taylor polynomial for the function f of x equals cosine of x at, and I want to do a equals pi over 3. Okay, so for a Taylor polynomial of a given order, that tells you how many derivatives you need to be at. So I need to compute f prime. Oh, let me just make a little table here. So f of x equals cosine of x, f prime of x is minus sine x, f double prime of x minus cosine x, f triple prime of x is equal to sine x. Okay, so I took 3 derivatives because I want the order 3 Taylor polynomial. Now, and I want to arrange it this way. Now what I'm going to do is I'm going to make a table here where on the right-hand side, I plug in my a value. So we need f of pi over 3. That's the cosine of pi over 3, which is 1/3. Sorry, not 1/3, 1/2. And then f prime of pi over 3, that's going to be negative sine of pi over 3, so that'll be a negative root 3 over 2. F double prime of x, f double prime of pi over 2. Sorry, I keep saying that wrong. F double prime of pi over 3, that's going to be negative cosine of pi over 3, so that will give us a negative 1/2. And then finally, f triple prime of pi over 3, that's going to be the sine of pi over 3, which is a root 3 over 2. All right, now that we have this, we can write down our Taylor polynomial. So this would be t sub 3 of x, and that's going to be equal to 1/2 minus, oh, I wish I had a little more room. I'll just try to write small. Minus root 3 over 2 times x minus pi over 3 minus 1/2 over 2 factorial x minus pi over 3 squared. And then, I'm going to have to write the last term down here, and then I'll clean things up. So this will be plus root 3 over 2 divided by 3 factorial x minus pi over 3 cubed. Okay, so here's sort of the initial setup, and then I want to make things look a little bit nicer here. But remember, for each term, you divide by n factorial. So technically, there's a 0 factorial down here, but that's a 1, and there's a 1 factorial over here, but that's also 1. Okay, so in final form then, t sub 3 of x is equal to 1/2 minus root 3 over 2 x minus pi over 3 minus 1/4 times x minus pi over 3 squared plus, this will be root 3 over 2 over 6, so that's a root 3 over 12, x minus pi over 3 raised to the third power. Right, so there is, in cleaned up form, here is the Taylor polynomial at a equals 3, order 3. Order 3 at pi over 3. Now, you might ask, what is this good for? And I've sort of tried to hint at the fact that the Taylor polynomial is an approximation of the actual function. So in particular, then, the point of this is that as long as you're near pi over 3, as long as the x value is near pi over 3, cosine of x and t3 of x are going to be close. And so let's just try that. Pi over 3, right? Pi is about 3.14, so this is close to 1, right? Pi over 3 is in the ballpark, it's in the vicinity of 1. So what I'd like to do is I'd like to compare t3 of 1 with cosine of 1. So what I'm going to do, I'm going to plug 1 into this polynomial and see what happens, and then compare what would happen if we actually plug 1 into, in the calculator. I'm going to do cosine of 1. And so it turns out t3 of 1. So plug a 1 in here and work out, do the arithmetic, and it comes out to be, let's see, t3 of 1 is about 0.540297. And cosine of 1 is about 0.540302. 540,302. Right, so it's not going to be a perfect match. It's an approximation, but this is a pretty good approximation, right? I mean, it's accurate to the first 3 decimal places, and then it starts to go off at the 4th decimal place. Right, so that's nice, right? And it's what we expect should happen, but this is sort of shows you that the Taylor polynomial gives values that are close to the actual function as long as you're near a. Okay, for our next example, what I want to do, so let's do, our function is going to be f of x equals square root of x. And just to save space, let me write the instructions right above here. So what I want to do, I want to find t sub 4 of x at a equals 4. And then use this to approximate, so let's say use this to approximate the square root of 5. So what's the idea? I want to compute the order 4 Taylor polynomial at a equals 4. By the way, it's just coincidence that 4 and that 4, I just happen to choose both those numbers the same. There's no reason. You can do 2 sub 3 at a equals 4 if you want. And then, so here's the idea. 5 is reasonably close to our a value, so I want to use the Taylor polynomial to approximate f of 5, right? So I want to compare t sub 4 of 5 with f of 5. All right, to do this, we need to take some derivatives, right? So this is x to the 1/2. So f prime of x will be a 1/2 x to the minus 1/2. F double prime of x is going to be a negative 1/4 x to the minus 3/2. F triple prime of x, so third derivative, that's going to be a 3/8 x to the minus 5/2. And then fourth derivative is going to be negative 15 over 16 x to the minus 7/2. All right, so if you're computing the order 4 Taylor polynomial, that means that you need to go out to the fourth derivative. Now we're going to plug our a value in, so I need to plug 4 into all of these derivatives. So first, f of 4, I have to square root of 4, which is 2. The next one, so let's see if I put a 4 in here, that's a 1/2, so that'll be f prime of 4 is 1/4. F double prime of 4, so now if I plug 4 into there, that will be what? Negative 1/4 times 1/8. Right, Right, so that's a negative 1 over 32. Third derivative will be 3/8. Well, let me just write it down. So it's 3/8 times x times 4 raised to the negative 5/2 comes out to be 3 over 256. And then finally, the fourth derivative, right? So plug 4 in here, and what you'll get is negative 15 over 2048. All right, once we have this list right here, right, now we can write down our Taylor polynomial. So t sub 4 of x is going to be 2 plus 1/4 x minus 4. Now remember, you divide each coefficient by n factorial. So we divided this one by 0 factorial, divided that one by 1 factorial. The next one will need to divide by 2 factorial. So this will be minus 1 over 64 x minus 4 squared. Then we'll have, so I need to divide 3 over, oh, sorry, what does that say? 240, what's that supposed to say? 240, oh, sorry, that should be 256. I don't know where I got the 245. 256. And when you divide this by 3 factorial, which is 6, you're going to get 1 over 384. So it'll be plus 1 over 384 x minus 4 cubed. And then finally, if you divide this term right here, this fraction, by 4 factorial, it comes out to be negative 5 over 16,384, and then it'll be x minus 4 to the 4th. So there is the Taylor polynomial. And it may not look pretty, but notice now what we're supposed to do is approximate square root of 5. Right? So t sub 4 of 5 amounts to just plugging 5 in to all of this stuff here. So that would be 2 plus 1/4 minus 1 over 64 plus 1 over 384 minus 5 over 16,384. And if you do this, right, you can do that very quickly in the calculator, and it gives me 2.236. So 2.2360229. And now if I plug square root of 5, right, if I plug 5 into square root on the calculator, it gives me a decimal, so square root of 5, 2.236, 2.23606, and so on. So notice, what do we get? We get a pretty good match. Those match those, right? So t sub 4 gives us a good approximation of the square root. So these examples here hopefully give you some feel for why you might be interested in Taylor polynomials, right? It gives you a polynomial approximation of a function, right, which you can then compute very quickly, especially a computer can compute very quickly. So we need to return to the question, when does f of x equal its Taylor series, right? So when does it have, now let's say it this way, so when does f of x have a power series representation and we know, right, if it has a power series representation, then it has to equal its Taylor series. So we can rephrase that, so we can say, i.e., when does this hold? Or when does the equation hold, where the equation is f of x equals sum n equals 0 to infinity, nth derivative at a divided by n factorial, x minus a to the n. All right, so we want to know when does this occur. Now, to answer this question, so let's let say r sub n of x equal the function minus its degree n or order n Taylor polynomial. So what does this r sub n, and this is going to be the remainder, of course, right? So this is the nth remainder. R sub n of x is the nth remainder as usual. And what does that measure? It measures the difference between the actual function and its approximation by this Taylor polynomial. Now, what would we want if we want, and remember, the Taylor polynomial, as n goes to infinity, right, as n gets larger and larger and larger, gets closer and closer to the actual Taylor series. And so what we want, if the function is going to equal its Taylor polynomial, then we would need this remainder to go to 0, right? And so that's our theorem here. If the limit as n goes to infinity of r sub n of x equals 0, then, and I need to specify on a certain range, so on or for absolute value of x minus a less than, what do I want to use? I guess just r. Think of it as the radius of convergence. So then, then f of x is equal to its Taylor series for all x within distance r of a, right, within the radius of convergence. Okay, so if we can show that the remainder goes to 0, then we can say that our function is equal to its Taylor series. So now we know if we can show that r sub n, right, so our goal, right, is to show that the remainder approaches 0, right? If we can do that, then we can conclude that the original function equals its Taylor series. Now, so we need a technique that will allow us to do that. And so this next result can be used to show that the nth remainder approaches 0 in certain cases, right? So this will be typically the theorem that we rely on. And so it goes like this. So theorem, and this has a name, it's called Taylor's inequality. And so it goes like this. So if the absolute value of the nth plus 1th derivative is less than or equal to some number m when x is within distance d of the number a, then the nth remainder, absolute value, is less than or equal to m divided by n plus 1 factorial times x minus a raised to the n plus 1 whenever x minus a is less than or equal to d. Right, so if you can find a bound, a maximum, this m stands for maximum, so think of this as the absolute maximum. If you can find a bound for the n plus 1th derivative, then you can find a bound for the remainder. And so then if you can show that this thing right here, which is definitely, you know, not much less complicated, right? If you can show that this goes to 0, that will then force this part to go to 0. Okay, so let's try an example of that. Remember, so let's say recall the Maclaurin series, which is just the Taylor series when A equals 0. So the Maclaurin series for the exponential function e to the x is sum n equals 0 to infinity, x to the n over n factorial. Radius of convergence equals infinity. So you can ask the question, is e to the x equal to its Maclaurin series? And to answer that question, what I want to do is I want to make use of Taylor's inequality. And so let's say it like this. Note that for any, let's say d greater than 0, we have, let's see, so we're supposed to think about the n plus 1th derivative, absolute value. So, well, okay, the n plus 1th derivative of e to the x, right, that's just e to the x. And that will be less than or equal to e to the d when absolute value of x less than or equal to d. So because the exponential function has such a simple form, right, and or I should say its derivatives have a nice form, right, when you take the derivative of e to the x, you get e to the x. This gives us an easy way to find our m value, right? The n plus 1th derivative is less than e to the d. So now we have that the nth remainder absolute value is less than or equal to m, which is this constant e to the d, divided by n plus 1 factorial times absolute value of x raised to the n plus 1. And as n goes to infinity, remember that factorial beats exponential. So this right here approaches 0, which means that the nth remainder approaches 0, which then allows us to conclude that e to the x is equal to its Maclaurin series for all choices of x. All right, so if you can show that the remainder goes to the 0, then you get to conclude that the function equals its Taylor series, or in this case, Taylor series at a equals 0. And so conclusion, we finally get to write e to the x is equal to sum n equals 0 to infinity x to the n divided by n factorial, and that is true on that interval right there for all values of x. As a quick application, if I plug 1 into both sides, we get e on the left-hand side equal to sum n equals 0 to infinity 1 over n factorial. So that's a nice sort of famous fact right there. Here's another way to think of e, right? It is, this series converges, and it turns out that it converges to the number e. Okay, so similar analysis shows that both sine and cosine equal their Maclaurin series also. So sine x and cosine x equal their Maclaurin series, which we computed last time. And so what I want to do now, I'm going to write a table here, and these are, I'll label this common Maclaurin series. And these are ones that you need to know. Right? These are the kind that you expect that you will have these memorized. So let me put them, and I'm going to just rewrite this one. The first one is the exponential one, right? These ones show up all the time. You need to have them memorized. So e to the x is equal to its Maclaurin series. Radius of convergence is infinity. Second one, let's do cosine. So cosine of x is equal to its Maclaurin series, sum n equals 0 to infinity, minus 1 to the n, x to the 2n, over 2n factorial, also with a radius of infinity. That means that for all x values, plug it in here, you get equality. Third one, let's do the sine of x. So sine of x equals its Maclaurin series, sum n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1, over 2n plus 1 factorial. Also radius of convergence equal to infinity. And then a few more that we've developed. So number 4, that's our geometric series. 1 over 1 minus x equals sum n equals 0 to infinity x to the n. And this one now has a radius of convergence of 1. So that holds as long as absolute value of x is less than 1. The next one, we also did this one. So arctan of x equals its Maclaurin series, sum n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1, over 2n plus 1. Also has a radius of convergence of 1, and it turns out that it converges at its endpoints also. So it doesn't really matter, but it is true that I can put a less than or equal to here and I still get equality. Right? It converges at both the left and right endpoints. Okay, what's next? Number 6 is, let's do this one. So, I don't know. You can do, I'll just do this one. So, it's nice to have one that involves natural log. Sometimes, I think your book might actually do natural log of 1 plus x. It doesn't matter. It's nice to have one that involves natural log so that you don't have to redevelop it all the time. Sum n equals 0 to infinity, x to the n over n. And that one has radius of convergence 1. And then there's one more that we're going to look at. So leave yourself some space here. There's one more that we need to talk about, right? And this will be Maclaurin series number 7. Right? So leave some space in between here and where your notes come next. Okay, so now let's take a look at that last of the Maclaurin series. And so we'll do this as an example. So let's consider the function f of x equal to 1 plus x raised to the k, where k can be any real number, right? Doesn't have to be an integer, doesn't have to be a fraction or anything like that. So, so we'll say where k is any real number. So for example, if k is 1/2, right, then we would be looking at that function right there, square root of 1 plus x. But we could also do k equal to square root of 2, 1 plus x, right, raised to the square root of 2. So any real number is legal here. Now, what I'd like to do is find the Maclaurin series. And so let's see what happens. If I do f prime of x, that would be k times 1 plus x raised to the k minus 1. F double prime of x, so then we would have k times k minus 1 times 1 plus x raised to the k minus 2. Third derivative is going to be k times k minus 1 times k minus 2 times 1 plus x raised to the k minus 3, and so on. Right, so this will keep going, and hopefully you can see that what this pattern looks like. It kind of looks like factorial, although k is not necessarily an integer, so we wouldn't call this factorial. Looks like my shot's a little off here. Ah, there we go. Sorry. That's not really any better. That kind of went too far. All right, so there we go. Sorry. Okay, so now we need, let's write down the formula for the nth derivative. And so how would that go? We'd go k times k minus 1, k minus 2. So we need to keep taking derivatives till we get to the nth derivative. So that's going to be k minus, now notice how the number here compares to this one here, right? It's off by 1. And so what it's going to be is k minus n plus 1. And then we'll have 1 plus x raised to the k minus n. Oop, k minus n. We want the Maclaurin series, so that would mean that we plug 0 in, and so that part's just going to be a 1. So what we get is the nth derivative evaluated at 0 is going to be k times k minus 1 times k minus 2 dot dot dot, and then eventually we get to k minus n plus 1. Right, there's the nth derivative. Now, of course, if we want the Maclaurin series, each of those coefficients actually then has n factorial in the denominator. And so there's shorthand notation for that, and it's written like this. So we're going to put a k in the top and an n here, right? This is often read k choose n. And what this is just a symbol shorthand notation for this following. K times k minus 1, k minus 2, dot, 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 k minus n plus 1, all divided by n factorial. And this will be the nth coefficient in the Maclaurin series for the function 1 plus x raised to the k. Now, and it turns out that this function will equal its Maclaurin series with radius of convergence equal to 1. And so we have, this is going to be number 7. Right? Remember I said leave a little space there. So number 7 is the binomial series. Is the name for it. Right? So put binomial series. And what we have is that 1 plus x raised to the k is equal to its Maclaurin series, sum n equals 0 to infinity. K choose n times x to the n. This equality holds for all values x whose absolute value is less than or equal less than 1. Okay, so there's number 7. Add that to the list, and now we have a complete list of common Maclaurin series. And now let's actually make some use of this. Right? Let's put this to work. So first, let's find the Maclaurin series. For what do we want to do? The function f of x equal to x squared e to the x cubed. Our starting point is going to be the Maclaurin series for e to the x. All right, so we know that is sum n equals 0 to infinity, x to the n over n factorial. The next thing I'm going to do, so remember what we do once we have a sort of a base of Maclaurin series, we can manipulate by substituting, by multiplying by x to the n. In this case, we'll multiply by x squared. And you should pay attention now. You've noticed how I've done these problems. You want to do your substitutions, your derivatives, your multiplications in the right order. So start off with a base. The next step should be, right, substitution. So e to the x cubed will then be sum n equals 0 to infinity, x to the 3n divided by n factorial. And then finally, I'm going to multiply by x squared, so x squared e to the x cubed. All right, that's equal to a sum. So if I multiply through by x squared, you just add exponents, it'll be sum n equals 0 to infinity. x to the 3n plus 2 divided by n factorial. All we did was a substitution, x cubed in place of x, and so still, right, the radius of convergence is going to be up strictly less than 1. So by starting off with our common Maclaurin series, we can do substitution, derivatives, antiderivatives, multiplying by x to the whatever power, right, to create new Maclaurin series. Next example, so let's do the same thing where I'd like to do, so our function f of x will be x times cosine of 2x squared. So start off with the Maclaurin series for cosine. X to the 2n over 2n factorial. So there's the Maclaurin series for cosine. Next step, I'm going to substitute. So cosine of 2x squared so this will be a 2x squared raised to the 2n divided by 2n factorial. I want to clean this up a little. So it'll be 2 to the 2n, x to the 4n divided by 2n factorial. Final step, I'm going to multiply through by x. So x cosine 2x squared okay, I just had a panic feeling. I think I said in that last example, I wish that it was still up on the chalkboard. I think I said that the radius of convergence was 1. I'm sorry, we were working with the exponential function whose radius of convergence is infinity. So please go back, change. When I substitute that x cubed, it did not change the radius of convergence, right? The radius of convergence of the exponential is infinity. Substituting x cubed does not change that. So the corresponding radius should be infinity. Sorry about that. Now, if I multiply through here by x, there we go. And once again, so the radius of convergence for this power series is infinity. Same with this one when you substitute. Okay, so now let's do our next example. And this one, like this, so f of x equals x over square root 4 plus x squared. And same instructions before, so what I want to do is find the Maclaurin series. And notice now we've got a square root here. This is going to be a job for the binomial series. And so I just want to manipulate this one a little bit. Remember, the binomial series requires a 1 there, so let's factor the 4 out. And then we can write it like this: x over 2 times square root of 1 plus x squared over 4. So notice what we have. This is starting like this. It's a binomial series where the k value is -1/2. Then x squared over 4 was substituted, and then multiplied by x over 2. So that's how I want to approach this one. Let's say g of x equals 1 over square root 1 plus x, right, which is 1 plus x raised to the -1/2. So then, yeah, I know that the binomial series tells us how to deal with the coefficients, but sometimes it's easier for me to actually just write them down or actually compute them to figure out precisely who these coefficients are, right? So we need the general form of the coefficients. And oftentimes for me, it's just easier to compute, right? So g prime, -1/2, 1 plus x raised to the -3/2. G prime of x, -1/2 times negative 3 halves times 1 plus x to the minus 5 halves. G double prime, that'll be a minus 1 half times minus 3 halves times minus 5 halves, 1 plus x raised to the minus 7 halves. Oh, and sorry, I got my derivatives wrong. That's a double prime and that's a triple prime there. So let's see if we can figure out what's happening here. We're multiplying fractions. It kind of looks factorial-like, except it's not quite factorial. Instead, what we're multiplying up in the numerator are odd integers only. So let's see if we can write down the general formula here. So for the nth derivative, yes, it's alternating, first of all, so there's a minus 1 to the n. And then, let's see, so we're multiplying 1 times 3 times 5 dot, dot, dot. And eventually we get to the nth odd integer, so that would be a 2n minus 1, divided by 2 to the n, right? Because there would be n copies of 2, n factors of 2 in there. And then it'll be 1 plus x raised to the minus 2n plus 1 over 2. So there's our formula for the nth derivative. Of course, we don't really care about this part because now I'm going to plug 0 in, right? We're doing the Maclaurin series. So gn of 0 that's going to be equal to minus 1 to the n, 1 times 3 times 5 dot, 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 2n minus 1 divided by 2 to the n, right? So there's a formula for the nth derivative. And now we have to be a little bit careful when n equals 0. This formula, let's see, does it make sense? It's a little weird when n equals 0. You always got to be careful with the 0th case. So that would be a minus 1 times minus, no, it would be a 1 times minus 1. So it doesn't quite work, right? This works when n is greater than 1. So what we have then, I'm going to be a little bit careful here. So 1 plus x raised to the minus 1 half is equal to 1 plus sum n equals 1 to infinity, right? My formula for the derivative kicks in when n equals 1. So I got to put the 0th term out front here. Minus 1 to the n, 1 times 3 dot, dot, or times 5 dot, dot, dot. Out to 2n minus 1 divided by 2 to the n times n factorial. Remember, you have to divide the coefficient by factorial. X to the n. Okay, so now let's come back to our original one. So let's see, in the steps, what we're going to do is next we substitute x squared over 4. So I guess we can write it like this, 1 over 1 plus x squared over 4, square root. Okay, that's going to equal 1 plus sum n equals 1 to infinity minus 1 to the n, 1 times 3 times 5 dot, 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 2n minus 1 over 2 to the n factorial times, okay, so if I substitute, so this will be x squared over 4 raised to the n. And let's fix that a little bit, so that's a 1 plus sum n equals 1 to infinity minus 1 to the n, 1, 3, 5, dot, 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 2n minus 1 over 2 to the n factorial, 4 to the n, and then we'll have an x to the 2n. Now, okay, I don't want to rewrite this, but I want to combine these because 4 to the n is the same as 2 raised to the 2n. And so I can join these together and get, if I add exponents, that'll give me a 2 to the 3n. Okay, so this is going to look like this. 2 to the 3n times n factorial, right? What did I do? 2 to the 2n times 2 to the n. Add the exponents gives me the 3n. The last step, I need to multiply the entire thing by x over 2. So, final answer, x over square root of 4 plus x squared. Multiply this entire power series by x over 2, and what we'll get is an x over 2 plus sum, n equals 1 to infinity, minus 1 to the n, 1 times 3 times 5, dot, 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 2n minus 1, x to the 2n plus 1, and then we're going to have one more 2 down there, so it'll be a 2 to the 3n plus 1 n factorial. Radius of convergence, absolute value of x over 4, I guess actually x squared over 4. So what do we have? Absolute value of x squared over 4 has to be less than 1, which means absolute value of x squared has to be less than 4. Take the square root. Absolute value of x has to be less than 2. So that one's a little bit more complicated, so I want to do all the steps there, right? They can be a little bit trickier when you're doing binomial stuff. Okay, I want to talk more about applications of this now. So, right, so why do we need Maclaurin series? What are they useful for? Well, here's one fact. So here's one reason why you might care about them. There is no nice formula for the antiderivative of e to the x squared. Seems like a fairly simple function, right? The antiderivative of e to the x is easy, but e to the x squared, it is impossible to write down a nice formula. So the next best thing is to recognize, oh, wait a minute though. We know that e to the x has a Maclaurin series. And so if we substitute x squared, we get a Maclaurin series for e to the x squared, and we can compute the antiderivative of that. We say, but, so here's what we get. E to the x squared antiderivative is equal to, if you substitute an x squared in here, what you'll get is x to the 2n. You get that. Now we can compute the antiderivative of the related, or the corresponding power series, x to the 2n plus 1 over n factorial times 2n plus 1. Don't forget your plus c. So, okay, we don't have a nice formula, like function style formula, but we do have a power series. Right? And this power series is exactly equal to that antiderivative. So now let's use that idea, and what I want to do is I'd like to approximate the integral from 0 to 0.1 e to the minus x squared dx with error less than 0.00000 1, 2, 3, 4, 5, 6. I want 6 zeros. 1, 2, 3, 4, 5, 6 zeros and a 1. Okay, so what do we do? First, we say e to the x has that Maclaurin series, which means that e to the minus x squared has Maclaurin series sum n equals 0 to infinity, minus 1 to the n, x to the 2n over n factorial. So what I'm going to do is take the definite integral of that power series, and then what you might be able to see is that we're going to get an alternating series, and I can approximate the alternating series to whatever degree of accuracy we need. So I'm going to compute the integral from 0 to 0.1, minus 1 to the n, x to the 2n. Oh, I need a sigma in there, sorry. Sum n equals 0 to infinity. Minus 1 to the n, x to the 2n, over n factorial dx. That's going to equal sum n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1 over n factorial times 2n plus 1, and we're going from 0 to 0.1. Plug in the limits, and I want to write it this way. So 0.1 is the same as 1/10, so I'm going to substitute a 1/10 in there when I actually write down the answer. So we get sum n equals 0 to infinity, minus 1 to the n over n factorial, 2n plus 1, 10 to the n, right? When you plug in the upper limit, that's what you get. When you plug in the lower limit, you get a 0. Oh, sorry, and it should be n right there, right? Sorry, I'm plugging into 2n plus 1, so it's 10 to the 2n plus 1. Make sure I got my answer matching up there. Yep. This is an alternating series, so if I want to approximate, I need to find the n that works. So let's find n, so that, remember we're doing alternating, so you substituted n plus 1. So I need 1 over n plus 1 factorial, 2n plus 3, 10 to the 2n plus 3, oh, capitals, less than, whatever that is, 1/millionth or something, 0, 0, 0, 0, 0, 0, 1. Thousandths, 10,000, 100,000, million, actually 10 million, so less than 1/10 million. Now, you can just try, if you try n equals 1, it doesn't work, but n equals 2 works. So check that n equals 2 works. So that's pretty small. And so what does that mean then? So integral from 0 to 0.1 e to the minus x squared dx is approximately equal to this series where instead of an infinity right there, I put a 2. So that would be, let's see, when n equals 1, what does that give me? When n equals 0, I get, there's a 1 there, there's a 1 there, so it's just 1/10. When n equals 1, I get 3 there, 10 cubed. Is that right? Yeah, so 1/3 times 1/10 cubed. Plus, when n equals 2, we'll get 1 over 2 factorial, so that's a 2. And then a 5, and then a 10 to the 5th. Did I get that right? When n equals 2. Yeah. All right. So that's a very nice approximation. Now there's one more, or that's very easy, right? I mean, there's not a whole lot of, why do I feel like I made a mistake here? Let's just make sure. Okay, when n equals 1, yeah, when n equals 2, that's a 5, and that's a 5. Okay, good. Okay, so this fraction right here approximates the definite integral with error less than 1/10 millionth. That's pretty amazing. Just 3 terms are required to get that accurate of an approximation. A couple of more examples. So here's another reason that you might want to know about Maclaurin series, because it will allow you to approximate definite integrals that you would not be able to compute using antiderivatives. You just can't do it. So Look at a couple more examples. Let's find the sum. And it's going to be sum n equals 0 to infinity, 2 to the n over 3 to the n factorial. You can show using the ratio test that this series converges, but at this point, or up until this point, we didn't have any way to actually find the exact sum. And here's what you want to recognize. This should remind you, when you see n factorial, think exponential. E to the x is equal to sum n equals 0 to infinity x to the n over n factorial. So what is this series right here? This is equal to this series where 2/3 has been substituted in, which means that this is equal to e to the 2/3. That's it. If you can recognize, oh, this is a familiar Maclaurin series where some number has been substituted in, then you can find the exact sum. Let's try one more example. So find the sum, and this will be sum n equals 0 to infinity, minus 1 to the n pi to the 2n plus 1 over 3 to the 2n plus 1, 2n plus 1 factorial. This should remind you of a familiar Maclaurin series where something has been plugged in. In this case, it's sine, right? Sine of x is equal to sum n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So here's why you got to have your Maclaurin series memorized, so that you can actually recognize, this is a power series where pi over 3 has been substituted in. So this is equal to sine of pi over 3, right, which is root 3 over 2. So this series converges, and now we know exactly what it converges to. It converges to root 3 over 2. All right, that's enough for today, so we will see you next time.